Hello, we're going to look at 1.2, which is the last part of PowerPoint 1.1 and 1.2, slides 21 through 25. This last part discusses how to find domain and range of a graph, relations, and functions, as well as function notation and how to evaluate a function. You will see all of these concepts used as we progress into pre-cal as well as calculus. A relation is simply a set of ordered data put in pairs. So for example, if we're talking about the players on an MLB baseball team, we could compare, or we could even just list, okay, well, if on the Atlanta Braves, every player corresponding to their salary. Or, of course, it can be as simple as just a list of numbers. That's all a relation is. It just relates a set of data. For example, 2 is going to correspond with 7 and vice versa. They're paired together. A function, more specifically, is a special type of relation where each x value, or the first number, corresponds to only one y value. So for example, in this relation, notice how 2, which is your first value, or your x, is only paired with 7. You do not see 2 being repeated, meaning it would be paired with something else. So for a relation to be a function, no x can be repeated. That's a shortcut way to tell you. And we're going to look at different types of relations, how they may be represented. You can have a mapping, table of values. Mapping is one of the more abstract types of relations that you don't see a whole lot of. Or, of course, graphs and set of order pairs. All right, let's first look at this mapping. The first one I have has these x values, or as we'll see in a minute, that's also known as your domain, and set of y values, 6, 8, 9, also known as your range. Let's say, for example, that I pair 1 with 6, I pair 2 with 6, 3 with 8, 4 with 9. That's what a mapping looks like. Would you consider this a function or not? Notice once again that you can have no x repeated, meaning that no x value can be paired with more than one y. So then you need to think, well, is 1 paired with anything else besides 6? No. Is 2 paired with anything else besides 6? Once again, no. Some of you may be confused by the fact that 6 has an x corresponding of 1 and an x corresponding of 2. You can have a y value repeated. In order for it to be a function, however, no x repeated. So 1 is only paired with one of these y's, and so forth. A mapping to me is and a graph are the two of the easier components to see if they're a function. In the second mapping, let's say that I pair 6 with 1. Alright, as you can easily see in the second mapping, you've got 8 that is paired with 1, and 8 is also paired with 2. So in this case, we have an x value repeated. Same case with 9. 9 is paired with 3, and it's paired with 4. So this is not a function. This would be a function here. In the table of values, is this a function? Notice your x values. Do you see any repeated? No, we don't. So yes, it is a function. All right. Let's give an example of a table of values that would not be a function. Let's say that we have 5, 2, 5, negative 1, 9th, 6, 1, 5th. So in this case, of course, you see that you've got an x value repeated, so not a function. For your graphs, do you remember the lovely method that we use to determine if a graph is a function? It is called the vertical line test. So remember vertical line test. That simply means that in any graph, if you can draw a vertical line through any part of that graph, does it only touch once? So it can only touch one time for it to be a function. And if it touches more than once, of course, no, it's not a function. So of course this one is yes. I can draw a vertical line anywhere I want through that graph. But if I draw a vertical line here, of course it touches more than once. It touches here and here. So this one is not a function. And this one, I can draw a vertical line anywhere I want on that graph. And it touches only one time. So this one is yes. Okay, moving on. A set of ordered pairs that is a function. Once again, remember, if it is a function, no x can be repeated. So if we have 101, 109, 108, -4, as long as, it really does not matter what these y values are. As long as I don't have an x paired more than once, then yes, it's a function. Not a function. -10, -10, we can have -29. Once again, I've got an x repeated, not a function. Does not matter what the y's are in that case. Okay, the next part of 1.2, determining if an equation defines y as a function of x. And I am all about steps in math, most things we can apply a process to and follow. So in this case, step number 1, it'll be easy for you to see if you solve your equation for y. I'm not saying you have to follow these steps by any means. Solve the equation for y. And here is a very common thing that students forget on into math. I forget it myself sometimes. When you take the square root, for example, in part B, when we solve this for y, I will have to take the square root to get rid of that. You remember you put positive or negative square root when you do that. So step 2, if you can have more than one y value, then the equation does not define y as a function of x. So for example, in part B, when I solve this for y and I take the square root, I'm going to have a positive square root value and a negative square root value. So in that case, I would have 2 y values for 1 x, which cannot happen. And you're going to see that. It's kind of an abstract idea to try to wrap your brain around, but once you do several and keep practicing, you'll get the hang of it. Part A. Solve for y, subtract x squared. I want to move it to this side with 4. So 4 minus x squared. Then you think to yourself, if I plug in any number for x, like no matter what I plug in, am I going to get 1 value of y or 2 values of y? For example, if I plug in -5 and square it, notice I'm only going to get 1 possible value of y out. So in this case, it's yes. And I'm going to help you, I'm going to show you a shortcut in a second to help you easily arrive at your answer without having to do much work, which I know you guys will definitely be appreciative of. Part B. Once again, solve it for y. So subtract x squared, and we're going to have 4 minus x squared. You have to get rid of this exponent of 2 by taking the square root of both sides, and please make sure on this side you put the square root over everything. When you take the square root here, you're going to get positive or negative. I'm sorry. When you take the square root of y squared, you only get positive y, rather. I'm only going to get y. And if you'll recall your exponent rules in Algebra 2, remember we divide that exponent by that index number. Square root index is 2. So 2 divided by 2, that's how we're getting y to the first. Okay, anyway, on this side, I'm going to be left with a positive or negative root 4 minus x squared. Here, notice that if no matter what I plug in for x, and I'll show you an example out to the side, I'm going to have positive or negative. Let's plug in 1. If I plug in 1 for x and square it, I get positive or negative 3. 4 minus 1 squared, 3. Notice that y would equal positive root 3, and y would also equal negative root 3. Thus, I get 2 possible values of y, no matter what I plug in for x. So in this case, no. This equation does not define y as a function of x, because I get 2 values of y possibly out. I want to see if you pick up on the pattern as we progress from A through D, looking at the powers of y. Notice this was a first power, an odd. This is a second power, even power. Let's look at part C. Solving for y, subtract x from both sides, so we get 27 minus x. You have to take the cube root of both sides to solve for y. So this is going to leave you with y. Once again, divide exponent by index. And cube root of 27 minus x. Now, some of you may be wondering why we do not put a positive or negative in front of the cube root. You do not have to do that if it's an odd root at all. The only time we have to do that is if it's an even root. For example, if I have the square root of 4, well, the 2 possible values that can give me 4 are 2 squared and negative 2 squared. That's why even roots get a positive or negative. Odd roots do not, because you can type this in your calculator. Like the cube root of 8 is 2. The cube root of negative 8 is negative 2. So a cube root only has one possible answer. So in this case, no matter what I plug in for x, let's say we plug in 0 for x. 0 is going to make this become really nice. So just for example to show you, if I plug in any value of x, I'm going to plug in 0, get cube root of 27, and the cube root of 27 is 3. Therefore, I only get one value for y. So this one is yes. Part D. This problem, this one actually makes it easy. Which you're going to see in a second. You don't really have to do any work for these, and I'm not going to require you to unless you don't understand it. You have y equals just the negative root of whatever x plus 4 is. So once again, if I plug in any number for x, add 4, then I only am using the negative version of that root. So in this case, y would only have one value. So this one is yes. Notice in all of the functions that were yes, y had an odd power. Y had an odd power. In this case, y has an odd power, but you have to be careful here. This is actually an even root, but with them only taking the negative part, it's yes. If this was positive and negative, you would say no. And in part B, once again, that had an even power. So a shortcut is really going to be to look at the power of y. If you see a y squared in your problem and it does not specify to only take a negative or positive square root, I hope that makes sense, then it's going to be no. So even power, usually no. Odd power, usually yes. Okay, let's move on to function notation. Function notation, f of x, that's how you read that, or you can say the value of f at whatever value x is. This notation does not mean, I wonder if some of you can think about what I'm going to say next, does not mean multiplication. It does not mean multiply. It is not saying f times x. This function notation, you're going to see this a lot in pre-cal. You're going to hear me say that a lot, probably get tired of it. It's used to evaluate functions for certain values. So finding the value of f at value x. This is from your PowerPoint slide, one of the last ones from 1.1, 1.2. It says evaluate the given function for f of x equals 5x squared minus 3 root x. Part A, ask us to evaluate f of 2. So essentially, you're finding whatever the value of f is, or your y, for an x value of 2. You're really just finding an ordered pair of x and y in this case. So what we do, notice that x has been replaced by 2. So I take 2 and I'm plugging it into my function everywhere I see an x. So f of 2 equals 5 times 2 squared minus 3 root 2. Order of operations, please be careful here. You must do your exponents first before you multiply 5. I see a common mistakes a lot in that area. So 5 times 4, that's going to create 20 minus 3 root 2. There is nothing else you can do with this. Please do not say that that is 17 root 2. This is your final answer. The only time you can combine radicals into that is if 20 had a root 2 on it as well. So 20 does not have a root 2 tacked onto it. Leave it as that. All right, part B, f of 4. We're going to plug in 4 everywhere we see an x value. And simplify. Once again, do your exponents first. So 4 squared, 16. 16 times 5 is 80. Minus 3 root 4. And we can, of course, simplify root 4. I should have already done that. Root 4 is 2. And then multiply that to 3. So 80 minus 6, 74. So that answer turned out a little bit prettier than that one. This is actually taken from one of your homework problems. I don't know if this is an identical homework problem, but it's one very, very similar to your set. We'll look at, I'll work through A with you, but I mainly wanted to look at B and C. Please be careful with the negatives. Please be careful with squaring this binomial. So let's go ahead and look at g of negative 1 in part A. Evaluating this function for the given values of x. So once again, in this case, x has been replaced by negative 1. That should be g2, by the way. So we're going to take negative 1, plug in everywhere we see an x. Please, when you plug in negative numbers for your variables, put parentheses around them. That will help you with signs down the road. That turns into, you've got 1 minus 2, negative 1, plus 3 makes 2. Part B, my favorite type of problems that start taking it up a level. So we have x plus 5 squared plus 2 times x plus 5 plus 3. I had to take this whole chunk of values, x plus 5, and I had to plug it in everywhere that I see x. So I took x plus 5, plugged it in here for x, and we're going to square it. Took x plus 5, plugged it in here for x, and we're going to multiply it by 2. And then you have to make sure you remember the plus 3. Okay, so x plus 5 squared. A lot of people forget this, and please be careful. X plus 5 squared is also x plus 5 times x plus 5. There is sort of a shortcut method that you can use, or you can just do the FOIL method. If you can't remember, square the first, square last, multiply inside, double as your shortcut. We'll get to that later on. But so for the time being, make sure that you square binomials, FOIL method. So I just come out to the side if you need to and do this. So make sure you multiply the first terms together. X times x gives you x squared. Make sure you multiply your outer terms together. X times positive 5 is 5x. Inner terms, positive 5 times x is 5x. Last terms, positive 5 times positive 5 makes positive 25. Simplify that, combine like terms in the middle, you get x squared plus 10x rather, plus 25. Plug that in. So that is just that part. All we did was take that part and pull it out. So x squared plus 10x plus 25. Then we also have this part in the middle. You distribute positive 2 to both terms. So I have 2 times x gives me positive 2x. Positive 2 times positive 5, positive 10. And don't forget your plus 3 to bring down. Go through and combine all like terms that you can. You've got 10x plus 2x. And then positive 25 plus 10 plus 3. So 35 plus 3, 38. And there's no other like terms to combine. That's it. So all you're doing when you evaluate these functions, plug in, do your math, and just combine like terms. Okay, last one. I'll show you really quick how to do this one, and then we're going to move on to the next. So g of negative x. And there's a reason that we're plugging in negative x. We're going to get to that when we do even and odd functions in 1.3. Negative x squared turns into positive x squared. Whoops. And then we plug in, I have to take negative x and also plug in here. So plug it in both places. And that's going to give you minus 2x here and then plus 3. And that's as far as it can go. No more like terms, nothing else to do. All right, last but not least, part of this is domain and range, looking at graphs, finding function values. In 1.2 domain and range, once again, very important. I cannot stress to you how important these concepts are in chapter 1. We use them all throughout. Domain is your set of x values. Set of x values in a relation or function. When you're looking at domain on a graph, such as in this example and this example, your domain is always related to your x-axis. And it tells you how far left your graph goes and how far right your graph goes. And make sure you always pay attention if there's any gaps in between those areas. So domain, how far left and right a graph goes. It's the set of x values. Range is a set of y values, or how far up and down your graph goes in relation to the y axis. So in some of these cases, it gets hard to make yourself only focus on, okay, I'm finding domain, I just need to look at the x-axis, I'm finding range, just look at the y-axis. To list your domain and range of graphs, there's two different notations that you can use. One is called set builder, and I'll show you what that looks like. And the other one is called interval notation, which you should have learned about a lot. You should have used interval notation some in Algebra 2 Trig. Set builder notation, it's more of the abstract one that we don't use a lot. All right, let's say, or it'll look like this, just to give you an example. So, set builder. If we're talking about a domain, it'll say all x such that, that's what that bar means, such that. If you plan on majoring in engineering or mathematics, you definitely need to make sure you gather or get the vocabulary down. In this class and in calculus, you will see it a lot in college. And of course, I mean, for everybody, make sure you get the vocabulary down. So it'll say all x such that x is greater than or equal to 7. You can have all x such that x is between negative 200 and 100. Or you could say x is all x such that x is all real numbers. You remember double bar R? If you've heard Miss Rogers or me talk about that, or Miss Shields. Domain and range. So range, you could say all y such that. We'll say y belongs to the real numbers. I'll show you what that looks like here. This just says y is all real numbers. It's a little y belongs to the set of real numbers. Like I said, we don't use that one a good bit. Number 2 is your interval notation. And it looks like domain would be from 7 to infinity. I bet you guys remember that one a little bit better. Range would be all your y's from negative infinity to infinity. Just to give you some examples. Those are just random things that I just come up with. This is the last part of your homework problem set in 1.1, 1.2, that Word document. You need to make sure that you do all parts of those problems, because in your directions it said use the graphs to find the domain in part A, range part B, x-intercepts, y-intercepts, and missing function values for these graphs. So in this first example, all right, let's focus on part A, which is finding your domain. Once again, domain is in relation to the x-axis. You only are looking to see how far left this entire graph goes, how far right the graph goes. So if I'm following this graph along to the left and I'm only wanting to look at my x values, only look at your x, let's see, where does this graph end in relation to the x-axis? Well, it ends here, going left, So what is x value here? 0. So I'm going to start at 0, and you always, let's go back up here and make a note. List from smallest to largest. Very important. Can't tell you how many times I mark students wrong because they actually list the bigger part first. Always go in numerical order. So once again, it goes left to 0, and then let's follow the graph to the right. How far right does it go in relation to the x-axis? It goes to 5. And notice there's an open hole at 5. You need to figure out, do you put parentheses or a bracket around 0? Well, notice here, 0 is filled in. So I'm going to put a bracket. Notice it goes to the right to 5. 5's an open hole, so I'll put a parenthesis. So you definitely need to make a note. That's just for interval notation. So interval notation uses brackets with open holes. Uses parentheses with open holes and brackets with closed in. Do you remember the first part of Algebra 2 trig last year when we learned interval notation? Range for this graph, let's look at how far down the graph goes and how far up. So notice if you're looking at the y-axis, the graph goes down and stops at -1. So once again, we're only looking at the y-axis. You can turn your graph, like turn your paper if you wanted to, and then notice that it goes down to -1 and it goes to 5. But, alright, so it goes down to -1, that's the lowest part. Then it goes up, your graph does, to 5 on the y-axis. Do you put a bracket or parenthesis around -1? It's filled in, so we put a bracket. Notice that at 5 it was an open hole, so it gets a parenthesis. For your x-intercepts, you're just simply looking for where does the graph cross the x-axis. The x-axis is here. It crosses at 2. And we need to write that in ordered pair form. When you're on the x-axis, recall that y is always 0. X is 2. Let's look at your y-intercepts. Where does it cross the y-axis? Notice it crosses at -1. And when you're on the y-axis, what is your x value? Notice when you're on the y, x is always 0. And we put a bracket at -1 because it's filled in. Whoa, no, sorry. My brain is totally going the wrong direction with that. 0, -1. Just write it as an ordered pair. So my y-intercept is -1, so we write it 0, -1. And f of 3. So what this is asking you to do is actually find, this is f of x. So we're going to go to the x-axis at 3. They're wanting you to find the corresponding y value there. So go to the x-axis at 3. The corresponding y is 1. You're finding the value of f or y when x is 3. When x is 3, the value of y is 1. Now, sometimes you may be asked, and I think one of your homework problems, it asks you to find, I'm going to reverse it on you. So let's say that we were asked to find f of x for 1, and they wanted you to find x. Well, in this case, f of x or y is 1. So you would go to the y-axis at 1, and then you would go to your graph, wherever it's at, and then find that corresponding x, which would be 3. So x would be 3 in that case. So look out for that. Last but not least, this second part. Let's look at your domain first. Domain. All right, once again, recall domain is how far left your graph goes, how far right it goes. Your graph, does it ever stop going to the left? Notice these arrows indicate it's going to keep going down and to the left forever. So your graph is going left to negative infinity. The same case, it's going right forever to infinity. There's no gaps in the middle. Your range, how far down does your graph go? It's going down forever. How far up does it go? Notice that in relation to the y-axis, it's going down forever. And then it comes up, but it caps off at -2. Doesn't go up further than that, so -2. But do you use brackets or parentheses? Definitely use brackets here because, of course, you're laying right on 2. It is touching at -2. X-intercepts, there are none. Notice that your graph does not cross the x-axis anywhere. Y-intercept is -2. And we write it as an ordered pair with x is 0. And last but not least, let's find the function values at f of -4. These are your x's that they give you. So go to the x-axis, then you're finding your corresponding y value. -4. Go to where your graph is at. My graph would actually be passing through this point if I extend it on out. So -4, your y value is -1, 2, 3, 4, 5. That would be your corresponding y. This case, they give me an x of 4, so go to the x-axis of 4. Go to where your graph is at. The corresponding y is -2. And you can always double check this because it should form an ordered pair with your x of -4 and a y value of -5. So you can double check. Is that ordered pair -4, -5 on? Yes. So -5, -2. Okay, next class, or when we meet live, we will discuss, we'll practice some more with domain and range with some problems in the book that I'll show you.